let's practice using those techniques to find domains in this example here. So for the first one, we don't have any division. So no division means we don't have to worry about dividing by 0. Also, there's no square roots, so no roots, which means we don't have to worry about where this function x squared minus 9 is positive or negative, which means we have no restrictions whatsoever. So the domain is all real numbers, right? So you saw that notation on the Appendix A1 note packet. That just means real numbers. As an interval, you go all the way from negative infinity to positive infinity. So this R right here would be this set builder notation for this example. Next, we have this example over here where f of x is equal to x plus 4 over x squared minus 2x minus 3. We have ourselves a division, which means we need to make sure that whatever we plug in for x, that x squared minus 2x minus 3 does not equal 0. And we're going to flip this around a little bit to conceptually make it a little easier to understand what we're doing. So instead of asking where is this not equal to 0, why don't we find where it is equal to 0 and then just get rid of those values, because that'll leave us with everything that causes it not to equal 0. Now we need to FOIL this thing, or reverse FOIL, so factor it. So we need to have a positive and a negative, because this is a negative over here. We need numbers that multiply to 3. So 3 and 1 are the only ones that we have. And since this middle term is a negative, the bigger number goes over here, smaller number goes over here. Now we have two expressions that multiply to 0. Here is where that 0 product property comes into play. And so we take x plus 1, set it equal to 0, x minus 3, set it equal to 0, and solve these two equations. Right, so x is equal to negative 1, x is equal to 3. So first things first, we have to get rid of negative 1 and get rid of 3, because those cause this denominator to equal 0, which means that if x is not equal to negative 1 and it's not equal to 3, then the denominator is not equal to 0. So for the domain, first we'll do interval. We're going to go all the way from negative infinity to our first value, negative 1, and we don't want to include it. Then we want to go from negative 1 to positive 3. We don't want to include it. Then we want to go from 3 and include everything to the right of it. And to put these three intervals together, we're going to union them, which just glues those together. That is the interval notation for this domain. For the set builder, we're going to take all values x, for which x is not equal to negative 1 or 3. And that's sufficient here. Lastly, we have ourselves a square root. So we need to figure out where x squared minus 9 is non-negative. So it can equal 0 or it can be positive. Similar to what we did over here, we're going to factor this x squared minus 9. Right, that's a difference of two perfect squares. And we have two conditions. We have greater than 0 and we have equal 0. So we can figure out where this thing equals 0, right? 3 and negative 3. So those aren't interesting to us anymore. What I'm going to do is set up a table, which will make sense in just a second. All right, so these are the intervals where we get rid of -3 and +3. And of course I did not leave enough room. I apologize about that. But we have 3 things that we want to keep track of. We have x minus 3, we have x plus 3, and then we have what happens when we multiply these together. And when we multiply them, we get x squared minus 9. All right, so pick any of your favorite number from -infinity to -3. And think about what happens when you do that number minus 3. Is it positive or negative? For instance, if I take -4 and I subtract 3 from it, that gives us -7, so it's negative. If you take your favorite number, let's say -4 again, and add 3 to it, you get a negative number again. And since we're multiplying those 2 values after we plug in for x, we have a negative times a negative, which gives us a positive. All right, so I guarantee if you take -4, square it, and subtract 9, you get a positive number. That's all that plus sign is telling us. Pick your favorite number between -3 and 3. Let's go with 0. So if you take 0 and subtract 3, you get a negative number. If you take 0 and add 3, you get a positive. So if you did a negative times a positive, you get a negative number. And that is what it is. Pick your favorite number that's larger than 3. Let's say 242. And if you subtract 3 from that, definitely going to be a positive number. If you take 242 and add 3 to it, again, it's going to be positive. So if you have the product of 2 positive numbers, you get a positive outcome. Now we have this column, which we care about here, and we want it so that that column is with a plus. So we care about this one, and we care about this one. So our domain, we go from -infinity to -3. Now, for the square root, you can take the square root of 0. That's what that bar underneath the greater than symbol means. And so we want to include -3. We don't want anything between -3 and 3, because that gives us a negative value when you plug it into the function x squared minus 9. And so we want everything to the right of 3, including 3. You just glue those together. And then the set builder is a little bit trickier for this one. We're going to take the set x such that x is either less than or equal to -3, or x is greater than or equal to +3. And what this or really means is union. So you can break this one set up into x such that x is less than or equal to -3, close the bracket, union x such that x is greater than or equal to 3. But this way is a little bit easier to read. And that leaves us now with the different types of operations we can do with functions. So let's say that you're given function f and g with domains s and t, respectively. When I say the word respectively, the domain of f is s, domain of g is t. So our first operation is adding 2 functions, and that is going to be the sum function, f plus g. It's going to be defined by taking your input x and evaluating both at f and at g, and then just adding those 2. And we need to talk about the domain. So we need to be able to take the value x and plug it into f, which means that x has to come from s. We also want to take x and plug it into g, which means that x has to come from t. So the domain of f plus g is everything that is both in s and in t. And to represent that operation, that is the intersection of those 2 sets. The next way we can put functions together is the difference. which just like the sum, you have f minus g evaluated at x. It's the same thing as taking f of x, g of x, and then just taking their difference. And again, since you're plugging x into f, x into g, x has to be in both the domain of f and the domain of g, so that's s intersect t. Next, we can multiply two functions, and so that's going to be the product f times g, which is defined again what is called pointwise. So for each x, you plug it into f, you plug it into g, and then you do that extra operation of multiplying. And again, just like for sum and difference, it needs to be able to be plugged into both. So the domain is s intersect t. Then the last one, where you take f over g, that is going to be the quotient function. So you have f over g of x, just like all the other ones. You do f of x, g of x, and then you divide. Now, just like the three above, you need to have values from s and from t to be able to plug them into f and g. But since we have a division, we have to make sure that whatever we plug in for x doesn't cause the function g to zero out. So we need to take the set of all x for which g of x is not equal to 0, and also include that as one of our rules to define the domain.